That's the turning point. All right. The axis of symmetry is a line that splits the parabola into two equal parts. The zeros, the roots, the solutions, also known as the X-intercepts. And the average rate of change, which is also known as the slope. All right. So some of these are easier to find than others. The slope is kind of tricky because if you're dealing with a line, you have a constant rate of change, but in a parabola you have a variable rate of change. All right, so the average rate of change will be different depending on where you are on the curve. All right, so that makes it a little funkier. All right, but something like the axis of symmetry is pretty easy to find out visually because if you're looking at the picture, it would be the line that cuts the parabola in half. That would be right here. That would be my axis of symmetry. I'll call it A of S as an abbreviation. Just a visual representation. Now, if you have a parabola or an equation of a parabola that you need to graph, it could be a little trickier, right? Because if it's decimal related, you get some funkier values, large values, or maybe it's just problematic to graph it, then you're probably not going to want to rely on a graphical approach. You're probably going to want to go for a more analytic approach. Okay? So there is a formula, and the formula, I mean, it's not bad, but it's just another formula. Right? So the formula for axis of symmetry is x is equal to negative b divided by 2a. The negative b over 2a, those b and a values are the same b and a values that we were using in the last unit. So we get them the same way we would get the b and the a values for the completing the square approach or the quadratic formula. So it's the same general idea. The vertex is the turning point. It's the point in the graph where it turns around on itself. So that would be right here. All right. There's also a formula for that, because again, if you have to draw the graph anyway, it might not be a problem. But if you're just given an equation and you want to pull that information from the equation, you might want to use a rule. All right. So in that case, you would find negative b over 2a, and then evaluate the function for negative b over 2a. I got to fix those parentheses. All right, so that's function notation. We'll review that as we go forward, but what that's telling us to do is find the result of negative b over 2a, that computation, and then take that result and plug it into whatever your original function is. All right? So your quadratic function will be in the form, we're familiar with the ax squared plus bx plus c notation, but now we're saying that that's equal to f of x, not just always equal to 0. All right? So this would be a quadratic function. F of x is equal to ax squared plus bx plus c. The zeros, roots, or solutions, they all mean the same thing. Again, visually you can make that determination, but sometimes they're not clean values, also known as x-intercepts, but they're the points where they cross the x-axis. Right? So what we would do here is we would set the function equal to 0 and solve. Right? And again, that's assuming you can't just pick it right off the graph. In this case, we can. It's not bad. It's here and here. You got one there, and you got one there. All right, so this would be a root. This would also be a root. And then the average rate of change, that's just, again, it's the slope. It's change in y over change in x. All right, but it can be a little funkier when it comes to function notation. All right, so if you're given a graph and I need to find, let's say, the slope between this point and this point, all I'd have to do is go up and over and figure it out. So that wouldn't be too bad. But again, if I'm not given the graph or I don't want to create the graph, I would need some other method to figure out the average rate of change. All right, so the average rate of change is going to be the slope over an interval. All right, so slope from A to B. So the way we figure out the slope there is by evaluating the function for A and B. So we find f of B, subtract from it f of A, and divide that by B minus A. All right, that's equivalent to slope. Well, that's true, but what I meant to say was it's equivalent to change of y over change in x. All right, and I'll show you again how to handle that in a few minutes, because function notation is something that we did, but we haven't done it for a while, so we need a little refresher on that. But before we get into that, we'll do it by the graphs, by tables first, and then go from there. All right. So for number one, use the given graph, or using the given graph, fill in the corresponding table, and answer the questions. So it's not the best graph in the world, but you can pick out what you need to. We got to find the zeros. We got to find all the stuff that we just reviewed. The vertex, determine if the vertex is a maximum or a minimum. It's kind of a weird question, but when we get there, I'll explain. Equation of the axis of symmetry, average rate of change, y-intercept. We didn't really talk about that, but it's the point where it crosses the y-axis. That's usually kind of self-explanatory. What's the sign of the leading coefficient? All these other questions here. So let's just take it a bit at a time here. The zeros of the function, also known as the x-intercepts, would be the points where the graph crosses the x-axis. So looking very closely and carefully, I see that it crosses here at 1 and 3. All right, so that would be x is equal to 1, x is equal to 3. All right. Throw a little or symbol in there, because this is really, we spent the entire last unit figuring out zeros of a function, or x-intercepts. We just didn't really talk about it in that context. Right? But that's what we were doing. So x could be either, to get a zero of this function, or an x-intercept, x could be either 1 or 3. Right? The vertex seems to be 2, -1. All right, it's an ordered pair, a coordinate. All right, it's the lowest point on the graph or the highest point on the graph. All right. The thing about parabolas is that they're generally infinite unless they're restricted. And you'll see that this kind of is a little inconsistent from textbook to state exam to online resource. Some resources use arrows to indicate that the graph goes on forever. Others just kind of let it go off the page and say that if they don't have a hard stop, that you just assume that it goes on forever. Right? So we've got to kind of be prepared to interpret it either way. So this type of graph is assumed to be going on forever because there is no hard stop here and here. If there are closed circles, endpoints at these locations, then we could assume that the graph stops, but it doesn't have that. So it's an assumed arrow situation, so it goes on forever. All right. So that vertex can either be the lowest point on a graph or the highest point on a graph, right? But the thing is, it's kind of weird because when you have arrows involved, it's like, well, there is no highest point to this graph, right? Because it goes on forever. There's no definite maximum value, right? Because it's always in motion. But there is a definite minimum value. So when they ask, is the vertex a maximum or a minimum, they're saying just that turning point. Would that turning point be in the highest part of the graph or the lowest part of the graph? In this case, it would be the lowest part of the graph, so it would be a minimum. All right, the equation of the axis of symmetry. We don't need a formula for that. Again, we just eyeball it. It's a vertical line in this case that cuts the parabola right down the middle. All right, I'll make it a dashed line. All right, but they're asking for the equation of that line. And vertical lines always are in the form of x equals. So it's just a question of x equals what? Just count boxes. X equals 1, 2 units. So x is equal to 2. The y-intercept, just a 3. Crosses the axis, the y-axis 3 units above the origin. Now, this one's weird. It's what is the sign of the leading coefficient? Because we have no basis to make this determination yet. But I have to give you some information in order for you to know how on earth to answer this. So going back to the f of x is equal to ax squared plus bx plus c. If the a value is positive, it opens upward, the parabola. If a is negative, it opens downward. All right. So you can determine the sign of the leading coefficient based off the orientation of the parabola. Les? So in this case, the parabola is opening upwards, so the sign would have to be positive. For G, it's saying state the interval or intervals over which the graph is increasing. All right, increasing is the part where it would be going uphill. All right, so let me get my highlighter out. That would be this part. I mean, it's been a while, but you may remember back when we were talking about domains and ranges and increasing and stuff like that. One of the things I mentioned at the time was that we read the graph from left to right. All right, so as you read the graph from left to right, it would be decreasing if you're going downhill. Like if you're traveling along this path, what part would you be going downhill on and what part would you be going uphill on? All right. You could also look at it as which parts would have positive slopes and which parts would have negative slopes, but I like the uphill downhill analogy better. So when I state the interval over which the graph is increasing, I'm just taking the x values for which the graph is increasing, right? So the start and stop. When does it start increasing? When does it stop increasing? It starts increasing when x is equal to 2, and it never stops increasing. So all the way up to infinity. There's a solid point at 2. Infinity always gets parentheses. All right. So that was that bracket parenthesis stuff. So interval notation, if you remember, you always indicate the start and stop of the interval. And the fencing, whether you use parentheses or brackets, is determined based off whether there's an actual point there. So if there's a solid point at the particular number, then it gets a bracket. If not, then it gets parentheses. Okay? So for H, same idea. So let me go. I guess this color's fine. Decreasing would be the part where it's going downhill. I would ask myself, when does it start going downhill? The beginning of time, because that's what that arrow says. It's going to the left forever. It's going up forever. But more importantly, it's going to the left forever. So that's negative infinity. And when does it stop decreasing? Well, it stops decreasing once it gets to the vertex, which is at 2. And there's a solid point there. All right, the increasing, decreasing type of question should be pretty easy. Like at first glance, maybe not. But as we do more, you'll see that it's always going to be increasing and decreasing around the vertex. So it'll either be increasing into the vertex and then decreasing coming out of it, or decreasing into the vertex and then increasing coming out of it.
So, like, I just understand because, like, from when it's increasing, it's. Oh, never mind. It makes sense. Sorry. I was reading it wrong.
No problem. No problem. So then for I, we're up to I. What's the average rate of change for the following intervals? So that's where we find the slopes. Now, these bracketed intervals are x values, right? So this is saying from an x value of -1 to an x value of 0, right? So if I go to my graph, I'm going to kind of move all this stuff because it's getting a little busy right now. I'll put it back in a little bit. But if I find my x value of -1 and see where that corresponds with the graph. So here's an x value of -1. I look, any point along this line would be an x value of -1. I want the point that corresponds with the graph. So that would be this point right here. All right. And then also add 0. All right. So I want any point along this line here when x is equal to 0 that corresponds with the graph. All right. So that would be this point right here. So I'm looking for the slope connecting these 2 points. All right. So that's what I'm looking for I. Well, I and then lowercase Roman numeral 1. All right. So I would need the slope between -1,8 and 0,3. All right. So I need my change in y over change in x for those 2 points. So 3 minus 8, 0 minus -1, so 0 plus 1. So we're going to get -5 up top and a 1 on the bottom, so it's just -5. All right? That's also what you would have gotten if you did rise over run. You're counting down 5 boxes and over 1. So then they want us to go from 0 to 1, all right? So any point along the line where x is equal to 0, which we already have, to any point along the line where x is equal to 1. All right. So here's the line where x is equal to 1. I want any point along this line that corresponds with the curve or coincides with the curve. That would be this point right here. So this is what I'm looking for in I, Roman numeral lowercase Roman numeral 2. All right. So the point here, we have 0, 3, but the other point is 1, 0. All right, so again, it's change in y over change in x. 0 minus 3, 1 minus 0, that's going to give you a negative 3. All right, so that's getting across the idea of the variable slope throughout the curve. So it's not going to be the same slope. It's going to change depending on where you are along the curve. All right. Then they want us to go from 0 to 3. All right. So we already have 0. 0 is it's weird, but 0 has coordinates of 0, 3. And we're looking for the other ordered pair when x is equal to 3. So x is equal to 3 over here. Any point along this line has a value of x equal to 3. I want the one that coincides with the curve, and that would be right on that the x-axis there. So that would be 3, 0. So I'm looking in this case for this line segment. All right, and so 0 minus 3, change of y over change in x. 0 minus 3, 3 minus 0. Negative 3 over positive 3 is going to be a negative 1. And then the last one is 1 to 3. I actually don't even like these last two questions, because I like the ones that go along the curve. They tell more of the, let's do 1 to 2 instead of 1 to 3. Yeah, because you wouldn't know this yet. We'll get there, but there isn't a whole heck of a lot of meaning for the slope from one part of a parabola to the other. So pre-turning point and post-turning point. When you're on the same side, there's a lot of meaning, but when you're not, when you're on the same half, there's a lot of meaning. When you're not on the same half, it's different. So anyway, so 1 has a coordinate of 1, 0. We got that in 2, in Roman numeral 2. Now 2. 2 is our turning point. All right, if you go here, any point along this vertical line that coincides with the parabola would be what I'm looking for, and in this case is the turning point. All right, so that would be 2, negative 1. So my slope here, change of y over change in x, is going to be negative 1 minus 0 over 2 minus 1. So negative 1 up top, and then a positive 1 on the bottom, so just a negative 1. All right. And so that would be this little segment here. Yeah, I'm going to get that Roman numeral 3 out of there. It doesn't, like I said, it doesn't really bring anything to the conversation. And so I could bring this back in. But those are really the important pieces of the parabola. Now, the one thing you'll notice that we didn't talk about was the table, because honestly, we didn't really need the table. We had the graph. But they did say to complete the table, so. Test of the emergency broadcast system. Okay, I don't know. Going home early.
School canceled for the rest of the week.
Yeah. Early spring break. Double spring break. I don't know. The worst thing they could do to a person like me is give me hope.
No, don't do that. Don't give me hope.
No.
Possibly today.
Yeah. Not first period. I can't do that. Now I'm thinking about it the whole rest of the day. You know. So. Yeah. So the table of values, you just pull that right from the picture. But there are some things that you could get from the work that we did. You know, like the roots and the turning point, although the turning point's already in there. But if you just figure out how many values there should be and what, you know, what's given, what should be there, and you can kind of fill in the blanks. Like these, I'll say clearly are supposed to be consecutive values. If you count from -1 upward, you get 0, 1, 2, then 3, then 4, then 5. And so that part's not bad. So then we would just be looking for the coordinates that correspond with those values on the graph. So 0, we got a 3 out of that. 1 was a 0. 3 was also a 0, just looking for the y values corresponding with the given x values. And 5, well, that's not indicated, but there's a reason why they call this red line here the axis of symmetry. It means that it has to be symmetrical on either side of that line, right? So if this is a point here that's 3 units to the right of the axis of symmetry, then this point over here would also have to be 3 units to the right, right? So that's at 5. If we knew the height of this one was 8, this one was, I mean, it's hard to see, I'll write it again over here. This one was -1, 8. The heights would have to be the same. This one would have to be 5, 8. Even if you couldn't tell if it landed precisely on that point, it would have to. Just like this one was 0, 3. 2 units away from the axis of symmetry. This one is also 2 units away from the axis of symmetry with a height of 3. All right. Same deal here. Height of 0, height of 0. There's always that symmetrical aspect. Even for the decimal values, it's hard to tell what those are. But whatever this distance is, this one here, to the right of the axis of symmetry, this distance here would have to be exactly the same. Right? So we can pull that from the graph. But you could also pull it from the table itself, because once you realize that there's symmetry not only visually but numerically, that should help also, because these two numbers match, these two numbers match, and these two numbers match. All right? You have symmetry in the rows of your table as well as the graph. All right? So it's a nice little feature, because if you know part of the graph, you could always figure out the rest based off of the knowledge of symmetry. All right? That's a lot. I mean, when you look at it, I mean, this is all number crunching. We didn't do any algebra here, because you think about the instances where you're given an equation, the X-intercepts aren't clean, let's say they're irrational, and it's too much of a pain to make the graph. There will be instances where we have to use quadratic formula or completing the square to figure out the zeros of the function. Right? So this step here. But a lot of the other characteristics can be determined just based off of visual inspection.